So yeah, the subject is the name of the subject even itself is intimidating, right? Complex numbers. It's already like we're having a lot of weird feelings about it, I guess. But like, yeah, let's see where they came out from, and then from there we can see what are the applications, right? Because ultimately, if we can see some tangible applications, then we would be it would make more sense to try to learn this material, and that's kind of my focus on this like over the next 1.5 hours. So see what type of how we can benefit from complex numbers. To be honest, complex numbers is a can become it's a lot of material. I don't think I know the whole material, but I know some applications that I use like in a periodic way. So yeah, so let's start with that, I guess. All right, so let's first start with where it all started. So when you solve polynomial equations, sometimes sometimes it's easy to solve them and finding all the roots, right? So when I say polynomial equations, I mean polynomial equations whose coefficients are all real numbers. But sometimes we are stuck and we don't find we are not able to find any roots. Can you tell me a polynomial equation which you cannot solve in real numbers? Do you know any? Yeah, for instance, y equals 2x minus 1. I can solve this, right? So solving it means finding a solution for the case y equals 0, right? If I were to replace y equals 0, then that would be the roots. The solution in x would be the roots. And we can easily solve this. X is equal to 1/2. And we can depict it as well. So this is the x-axis on the Cartesian coordinates, x and y-axis. So this is a line in the complex plane. It has slope 2 and it is shifted down by 1. So something like that. So this is the root. It hits the x-axis at 1/2 and it hits the y-axis as -1. But the points where it hits the x-axis is considered as the roots of the polynomial. They are the solutions of the polynomial. Solutions means it solves it for y equals 0. When you plug in y equals 0, are you able to solve this? And you guys already suggested some polynomial equations you can solve it very nicely. Some of them you cannot solve it at all, right? So the equation that is very celebrated is this one. X squared plus 1 is equal to 0. Yeah, so for instance, this equation, yeah, so we won't be able to find a satisfactory solution to this one, right? It's kind of strange. Well, let me first draw the picture. The picture is this. So, whoops, it's a parabola that hits a minimum value at 1 on the y-axis, and then on the horizontal axis, it never hits the x-axis. And sometimes it's not convenient. So we kind of find ourselves wishing that, hey, I wish there could have been a solution. Sometimes you might have some higher degree polynomials, like a cubic polynomial, where even though there is one root, but because it's a cubic polynomial, I don't know, let's something ax plus b, let's say, oops. Ax plus b equals 0. Yeah, so you feel like you wish you could find 3 solutions. Why? Because I know very well that some polynomial, like some cubic polynomials, I can find 3 solutions. A cubic polynomial will not have more than 3 solutions, right? If its coefficients are reals, it won't have more than 3 solutions. So that's kind of in the back of our head. And it's kind of annoying too. For instance, compare this one to x squared minus 1. It's so easy to solve x squared minus 1 is equal to 0. Why? Because we can simply factorize this. X minus 1, x plus 1 equals 0. and as a result, we can get the two roots. The roots are x is either equal to -1 or it's equal to +1. Yeah, so this is kind of the backstory of all this thing. And indeed, that's how the discussion begins, actually. Why don't we just assume that it exists? And that was the first time that it all started. So if you go back to this one, let's try to solve it all the way. So x squared plus 1 is equal to 0. Well, technically, I'm supposed to take that 1 to the other side. Well, an alternative way to solve it would be the following, this one. X squared is equal to 1, and then we can go ahead and take the square root of both sides. The square root of x squared is what? Yes, that would be plus minus x, because I don't know the sign of x, right? So if it's negative, regardless, it should come out as positive out of the square root. The right-hand side is a 1, so which means x is equal to plus minus 1. So we can use a similar strategy for this one. Let's go back to our equation. So x squared is equal to -1. And why don't we just take the square root of both sides? I guess, yeah, that's kind of where it all started, right? And then on the left-hand side, the square root of x squared is just plus minus x, if you will. Yeah, let's just write it like that. Plus minus x is equal to, or you can write it as absolute value of x. It doesn't matter. So, sorry, that's equal to square root. And now we can move that plus minus sign to the other side. Plus minus square root of -1. So now, this is a human construction, right? So God created the integers, but who was it who said that? God created the integers, everything else humans created. So this one is definitely a human creation, right? So we can just relabel this as I. So suddenly this is plus minus I are the roots of x. Now, even though it's absurd, right? So the letter I represents imaginary numbers, as we call it. So look at that. I mean, it doesn't cross the x-axis, and now we are in another realm. We are suggesting that it does cross the x-axis. Yeah, the code is from Kronecker. Okay. Yeah. Yeah, so it's kind of, but then the same thing would apply to negative numbers as well. How real are negative numbers? Like a number like -2 or or minus √2. So, well, these are also real numbers. So, well, when I say real, I mean in the sense that, so even though at first it is kind of, you might imagine it's not very comfortable to think about it that way, but yeah, you guys can get, the more familiar we get with this, suddenly it turns out that this imaginary construction of this imaginary I, that number I, is so convenient. A lot of problems which are rather difficult if you don't use this concept turns out to be extremely simple when you use them. How do you graph functions on the Gaussian plane? Too advanced. Yeah, so let's think more about these numbers. So how do we represent them then? So one quick idea is the following. So from now on, any number, in general, it's customary to represent complex numbers with the letter Z. So we can just represent them like this: A plus bi, right? Because once you believe square root -1 exists, then 2 square root -1 also exists, right? So that would be 2i, and so on. But then similarly, 1 plus 2i also exists. So that's kind of the more generic form. So we can write complex numbers as such, where I is simply equal to square root of -1, right? Exactly, where A here is the real part, I should say, the real part of that complex number, and B is the imaginary part of that complex number. Awesome. But next, we need to find a good way to visualize it. How do I visualize all these numbers? Real numbers are easy to visualize. You can put them onto the real line. the real numbers, the positive numbers, all of them are here, right? 1, 2, 3, square root 2 is somewhere here, pi is somewhere here, e is somewhere there. So we need to find a convenient visualization of this, and we need, because now our number is kind of made up of two parts, a real part and then an imaginary part, we might as well put it onto the Cartesian plane. Yes, that's it. So, well, not Cartesian, complex plane, I should say. Yeah, the complex plane, that's it. So those numbers live in a plane where this is the real part of those numbers. This is the imaginary part of these numbers. So for instance, if you represent 1, 2, 3, 1, 2, oops. So the complex number here represents which number? So yeah, this is the complex plane. Yes, it would be 1, 2, 3, and then maybe you can call it 1i, 2i, and so on. Or you can, yeah, okay. So this would be 3 plus 2i in a sense, right? And yeah, so that's convenient. And then after a while, you start thinking more about these numbers. We can introduce some facts about these numbers, some properties. And then once I introduce these properties, then life is pretty good. Then we can start building up a lot of tools using these, right? So yeah, okay, good. So for instance, one of the things that I'm curious about is what? What do I want to know about 3 plus 2i? Oh, for instance, yes, we might want to know how to add two complex numbers. For instance, if this is 3 plus 2i, and then I have 1 plus i here, one thing that I'm curious about is how can I add these two complex numbers? On the real line, it's easy to add them. On the complex plane, how do I add them? Yes, we add them component-wise, yes, meaning vector addition, or you can just call it component-wise. So we can just add the real parts, and then we can add the imaginary parts to each other. So 3 plus 2i plus 1 plus I as a result is simply equal to, the real parts are 3 and 1, the imaginary parts are 2 and 1. So as a result, that would be 4 plus 3i. Yeah, so, and then when you look at it, it is somewhere there. But really, what you guys said is correct. It is as if we are adding vectors. Component-wise adding is the same as adding vectors. So it is as if, let me explain what I mean by that. It's as if I have this vector here, and then I have this green vector there. When I add these two vectors, either you can complete into a parallelogram, or so which is traditionally what we do. So all I do is I carry that red over here, and then the green over there, and that's it. So this shape is a parallelogram, and so you can shift that red vector onto that green one, and boom, so you get your the final result, which is 4 plus 3i. All right, so but you don't have to know anything about vectors. All you do is, yes, translate the red complex numbers, add it on top of the other one. That's the meaning of adding it the way we do. Another thing we might be curious about is how to multiply them. But it's the same thing, right? So if we try to multiply them out, let's say 3 plus 2i, and multiplying it with 1 plus i, we will just use the distribution rule, right? So we might as well just distribute, so the foiling it. So we can distribute the 3 first, so 3 plus 3i, and then 2i plus 2i squared. Aha. But wait a second. What is I squared? Something that we failed to mention. Yes, okay, we'll come to the magnitude in just a minute. Yes, because I by definition is equal to square root of -1, if I were to square both sides, I would be -1, right? So therefore, this is a real number, this is -2, so 2 times -1, right? So, so as a result, we have 1, 3 minus 2 is a 1 plus 5i. There you go. That's very convenient. I need to remind you of one thing quickly. A lot of students, this would be wrong so if, because I asked you I square a minute ago, I square, you cannot do it this way. You cannot say this is, hey, this is just square root minus 1 times square root minus 1. Hey, I can just bundle them inside the same square root, minus 1 times minus 1, and boom, I got square root 1, which is 1. There you go. Holy, they are not the same. Yeah, you can't do that, okay? Don't even think about it. All right, this is wrong. So you are not allowed to, for complex numbers, you're not allowed to like put them into the same square roots this way, okay? All right, so this is wrong. Yeah, this is correct. This is good. Check. This is not good. All right, so the square of I is minus 1. So just to be aware, like, so we want to make sure we're not messing up anything. How about dividing it by each other? 3 plus 2i, can I divide them? Such an operation, does it exist? How can I do that? How can I divide a complex number by another complex number? So far we saw addition, subtraction, multiplication. How would I accomplish division? Yes, I would try to rationalize the denominator, and somehow I kind of know how to rationalize it, remembering earlier that, well, okay, so you guys already, it seems a lot of you already know how to do it. You would multiply the denominator with something called its conjugate. So if you have z is a plus bi, then its conjugate, we usually use the z bar here. It's a minus bi, which is just a reflection across the real axis. Yes, a real part. Again, the imaginary part, imaginary axis. So a plus bi is this point here, where this is, oops, this is a, this is b. So this is, oops, a plus bi. So as a result, a minus bi would be somewhere there. It turns out to be extremely convenient. Whenever you multiply z and z bar, you get some really nice stuff. But let's do it just as an experiment here. If I were to multiply both the numerator and the denominator by 1 minus I, let's see what we get. The numerator is easy. Again, we FOIL it. Well, as we do in the denominator, both of them. So let's just do it. So 3 minus 3i, and then 2i plus 2i. So distribute the 2i minus 2i squared. And then in the denominator, we have 1 plus I times 1 minus I. But this is just a difference of squares. This is just 1 minus I squared. So as a result, but earlier we established that I squared is just minus 1. So minus 1. So that the denominator will be 1 plus 1. Let me just do it again. So 1 minus minus 1, right? Because I squared is just minus 1. And in the numerator, we will get 3. And then this is also a real number. I squared is minus 1, so that's a 2. So 5. And then we still have minus I here. So ultimately, this is 5 minus I over 2. Or if you will, you can write it as 5 over 2 minus I 1 over 2. Or 1 minus 1 over 2i. So clearly, the real part is 5 over 2. And the imaginary part of this complex number is minus 1/2. So because it turned out to be so convenient to multiply the denominator with something called its conjugate, we might want to just explore this product further in a more abstract way. Let's just go ahead and do that, I guess. So if we explore this, z times z bar, let's see what do we get. So we have a plus bi. If I were to multiply it with a minus bi, let's quickly check that. Well, this is obviously a difference of squares again. A square what? A square minus bi squared, right? So something like that. Yes, which is a square minus b square I square. But earlier we established I square was just the minus 1. So that's just a square plus b square. Yes, but suddenly, when you look at the geometry of this, a square plus b square is just the length of this blue section here, the length of that vector there. So which means, well, square root of it, square root of a square plus b square. So we might as well just use the absolute value sign again, right? So that would be absolute value of z squared, the magnitude of z square in a sense. That turns out to be a very important identity as well. So let me write that down. Z times Z bar is equal to absolute value of Z square. So don't be intimidated. I know some of you guys are new to this stuff. This is a high school subject, but we will see some useful applications in just a minute. You don't, most of this stuff, I'm just showing it because yeah, it's customary to do that, but just hang on, okay? So don't give up. All right, so, oh, one more thing. Now that we looked into this, let's, how about geometrically, let's have a look at the geometry. So a little bit more. 1 over Z. Where do I find 1 over Z? Let's have a look at that, or you can call it Z to the power minus 1, right? 1 over Z, where is it? Yeah, the inverse, the multiplicative inverse of Z. Yeah, so this would be, well, let's use the same trick that we just learned. Let's just multiply both the denominator and the numerator with Z bar. And then, so we find that this is Z bar over Z square, the magnitude of our complex number square. You guys see that? Interestingly, what it means is the following. So if you have Z somewhere there, Z, and let's assume that Z bar is just, say, greater than 1, let's say, for the fun of it. So then Z to the power, so 1 over Z, if you are curious where 1 over Z is located, well, it is located exactly where Z bar is located. Let me rewrite this like this. Z squared times Z bar. You guys see that? So this is just a real number, right? It's just a number, a real number. And you are multiplying it with this. So Z bar, we already know where it is. It is the reflection of Z across the x-axis. So this is Z bar, where this distance is equal to that distance, right? So as a result, because if we assume for the time being that Z is greater than 1, then 1 over Z will end up being somewhere here, for instance. Depends. If Z was less than 1, then 1 over Z would have been somewhere over on that side. It all depends on what is the magnitude. And interestingly, some of you guys already suggested it. If the Z has a magnitude of 1, this is the most interesting case, then necessarily 1 over Z is the same thing as Z bar. Now this, let's have a look at that. All right, so basically we are saying that this as a graph, this is what type of a graph? It is a, this represents what? On the complex plane. Yes, the real part, the real axis, the imaginary axis. Yes, it is just a circle. Why? It is all the complex numbers whose magnitude is 1, right? And by the way, so for instance, like this, let's say 3 plus 2i. So you can use a similar logic to figure out what this would represent, right? So anyhow, but let's go back to our question at hand. There you go. So we have 1i minus 1 minus I. Do you guys see that? So yeah, that's pretty good. So this is called, as you are right, this is called as the unit circle, right? On the complex plane. This circle is really cool. And for the first time, you will see the power of complex numbers. So far, we just introduced some new notation, and it is kind of, it's not even clear if it means anything yet. But now you will see for the first time what is the power of this whole thing. So on the unit circle, you can have any complex number like this, Z. Well, it will have a certain representation, right? All I need is to check what is this number over there, what is this number over here, A and B here, right? But yeah, this is not a very good way to represent this number, this complex number. There's a way more powerful way to represent a number, a complex number on the unit circle. Yes, where a squared plus b squared is equal to 1. Yes, I need to put that qualifier here, right? So because the radius here is a 1. That's right. So this is a 1 here. Well, there's a way better way to have a look at this, and it is by considering this angle over here. something which if you are in high school, you might have seen it before. Yes, you can put it in trigonometric form, right? So you can write this, you can represent A and B in terms of that angle over there, that angle theta. And it turns out that A is just what? Cosine theta, right? And similarly, B is just sine of theta. And I still have the I keep the I. But because the I and the theta, it will be confusing. I don't know if they are together inside the sine. So usually it's customary to just write it like this, like that. All right. So that's pretty cool. Now, okay, so what's cool about that, you might ask, right? So what's cool about this? Well, it turns out the cool thing about this is multiplication. Addition, it's not cool to use this polar form or this trigonometric form. It doesn't make sense. Complex numbers, the reason you learn complex numbers is really to rotate the objects in space. So maybe I should have given you this example to begin with. I even worked out a couple of numbers. So for instance, let's just solve. So right now everybody can follow up again. I think like for instance, if I ask you, okay, so quick question. If I tell you that, hey, we have this point here, the x-axis, the y-axis, and then suppose that we have this point 3, 2 here. 1, 2, let me first draw a grid before I go further. Check this out. And now you will see one of the benefits of learning about complex numbers. So for instance, this point here on the Cartesian plane, that's 3, 2, where this is the origin O. And what if I was asking you guys to rotate that point around the point, say for instance, 1, 1 by let's say 45 degrees. How would we accomplish that? So what I mean is you want to rotate this by 45 degrees, and so it will fall into somewhere, a new point. I don't know what point. I don't know. Well, actually, I have no clue where it will fall to. Maybe somewhere here. I don't know. So what is the coordinates of this point, AB? How would we do that? Let's not use complex numbers. And then let's solve the same problem using complex numbers. So I want to rotate it by 45 degrees. That point around the point 1, 1. So as a result, this distance will be equal to that distance. How would you do that? No. Like solve it. What do you call it? Solve it analytically. How do you analytically solve this? Like setting up yes. Yeah, okay, so some of you guys realized it. Because these distances are equal, then so what can you do? Like how can you set up equations in order to find A and B? Yeah, I think one way you can use the distance formula, right? We can just calculate the distance from the point 3, 2 to 1, 1, and then from the point AB to 1, 1, that would, like, at least we would know that we are fixing, yes, we are fixing, the lengths are fixed at least. But then I didn't make use of the angle yet, but that's a second equation. If you just use the distance formulas, for instance, the distance between 3, 2 and 1, 1, and then the distance between AB and 1, 1, you just set them equal to each other. So the distance between 3, 2 and 1, 1 would be 3 minus 1 square plus 2 minus 1 square. And the distance between AB and 1, 1 would be A minus 1 square plus B minus 1 square, right? You can just square both sides. That's a 4, that's a 1. So 5 is equal to A minus 1 square plus B minus 1 square. But that won't be enough. I need one more expression that I can use, right? So at that point, yes, you need to use some trigonometry related to 45 degrees, right? Yes, so some of you guys are suggesting we should use law of cosines, which would work. Some of you guys are suggesting we should use law of sine, which I think would work. I was thinking to use the addition formula for the angle. Let me show you what. So this angle here is a 45-degree angle, right? So I was thinking that if you call this angle as theta, so obviously tangent theta is equal to what? Well, this is an alternative way. I think it's all equal to each other. Yes. Tangent theta is, yes, it's rise over run. Rise is 1, run is 2. Yes, it's 1/2. So then I can just turn my attention to that, or maybe I can use a highlighter, to that huge angle, theta plus 45, and I can recalculate tangent for that angle. But I can benefit from that point AB here, right? So all I need is this distance, and that vertical distance, right? So tangent, technically, tangent 45 plus theta better be equal to, well, b minus 1 divided by the run, which is a minus 1. Do you guys agree? But wait a second. I already know how to calculate the left-hand side using trigonometry. So let's first set up the left-hand side, which is just tangent of 45 degrees plus tangent theta divided by 1 minus tangent 45 times tangent of angle theta. And while tangent 45 is just a 1 plus tangent theta, we just calculated it, it's 1/2. 1 minus 1 times 1/2, which is equal to what? 3/2 over 1/2, which is just a 3. Aha, so that whole thing was actually a 3. So b minus 1 is really 3 times a minus 1. Now we can go ahead and use this system of equations to solve it for a and b, right? So for instance, 5 is equal to a minus 1 squared plus b minus 1. We replace it with 3a minus 1. So that would be 9a minus 1 squared. So 5 is equal to 10a minus 1 squared, which means a is equal to 1/2. Well, okay, let me do it in 2 steps because I'm gonna mess up again. So a minus 1 squared is 1/2, 5 over 10, which means a minus 1 itself is plus minus root 2 over 2, which means a is, well, I assume we are on the positive axis, right? So we are just looking at the plus 1. So a is 1 plus root 2 over 2. Do you guys agree? Because we are rotating in the 45 degree on the plus side, right? Yeah, okay, so pretty good. And now we can go back into this equation again. And so this way we should be able to find b as well. I think b comes out as 1 plus 3 root 2 over 2. Yeah, so something like that. Okay, but you guys can see how we had to use a system of equations, right? So first, make use of the lengths, and secondly, the angle, either using a manipulation like I did, or you guys can use law of cosine on this triangle. For instance, we can measure this segment between AB and 3, 2, and yeah, it will still be pretty bashy. All right, so now we have, I think we will have a chance to appreciate the complex numbers. Let's go all the way down. Let's first try to understand the algebra. Okay, so if I were to represent this z as such, and then suppose that we have another complex number, let's call it w, and it had, we can write it as cosine of phi or psi plus I sine psi. Let's just test it, all right? So if I were to multiply them, that's where the whole action is, right? So cosine theta plus I sine theta, I will FOIL it again, cosine psi plus I sine of psi. Well, let's FOIL it. So cosine theta plus cosine of psi, oops, that's a psi. And then I can multiply these two, which will give me a minus sine theta, sine psi. So that's the real part. And then we'll have an imaginary part, sine theta cosine psi, sine theta cosine of psi, plus what? Plus sine, yeah, sine psi cosine theta, yes. Sine of psi times cosine of theta. There you go. But then wait a second. Yes. Well, yeah, this is definitely pre-calculus. Yeah, sorry guys. Yeah, complex numbers is more like high school curriculum-ish. But yeah, so we were still having fun, at least, kind of. We just remember this from high school, that this is just cosine of theta plus psi. And this is I times, hey, this is just the formula for sine of theta plus psi. Holy, what it means is, so even if you are middle school, you don't understand this proof, don't worry about it. In a minute, it will be just geometry. Hey, this is just, okay, so Z was somewhere there, okay, and let's say that psi is somewhere here, multiply, sorry, W, I should say, where this angle is psi. All right, so multiplying these two ended up giving you a new complex number on that same circle, unit circle, where the argument, we call these angles as the argument, is just theta plus phi. Holy! So you end up somewhere here. This is W times Z. Obviously, it is commutative, so Z times W is the same as W times Z, where this angle, this whole angle is psi plus theta, or if you will, I added theta to psi here. Yay! It's just rotation, that's right. So multiplying two complex numbers on the unit circle is the same thing as just rotating it. Just add their angles with the horizontal axis. All right, so that should be very convenient, right? So, but then you might say, hey, this is very restrictive. How about two complex numbers which are not on the unit circle? What if you have two complex numbers which are not on the unit circle? Well, that's easy too. Because, okay, so let's have a look at complex numbers which do not live on the unit circle. So if you have a complex number, let's say 3 plus 2i, how can I represent it? Suppose that my goal is to multiply this with this one. Both of these complex numbers, they are outside the unit circle, right? One of them is way outside, like one of them is right here. The other one is 1, 2, 3, way up there. Okay, so let me just, hold on, let me just drag it down a little bit. There we go. All right, I don't need that. All right, so this is the real part. So the other one is right here. How do I multiply two complex numbers? So this is the grid. So one of them, they are both Z. I can call them Z1 and Z2, or okay, I'm lazy. Let's call Z and W again. Z here and then W here. There you go. So we have W here, we have Z here. How can I just multiply them? Let's see if there's a faster way to multiply them. Well, yes. So first we need to convert them into this polar form in a sense. But how do I convert this into a polar form? Or a trigonometric form? Because I know that it does not live on the unit circle, what I can do is I can find its projection onto the unit circle and then scale it by a scaling factor, right? And I can do the same thing here. Just find that Z, whatever point it corresponds to on the unit circle, and then I'm done. I now know this angle, I know this angle, and then I can just multiply the scaling factors. So let's quickly do it. So let's start with W. So how do I find where it hits on the unit circle? I can just divide it by its magnitude, right? So we can quickly check the magnitude of it, which turns out to be square root of a squared plus b squared. Yes, 1 squared plus 1 squared, which is a root 2. Aha. So therefore, I can really rewrite it in the following way. If I factor out the root 2, what will be left inside will be this, I over root 2. Why in the world would we want to write it like this? Because this thing here is exactly that point over there. Now, it obviously, the reason we did it like that, so that is to calculate the angles. So what is the angle? Root 2 times, okay. Because remember, the real part is the cosine and the imaginary part is the sine. Yes, the angle will end up being the 45-degree angle. So this is really cosine of 45 plus I sine of 45 degrees. There you go. Some people, they just, for convenience sake, they just express it like this, CIS 45. It's the same thing. Okay, so C, the first letter of cosine, I, and then CS, the first letter of sine. So that's an alternative way to write that same thing. But it's kind of confusing. If it's confusing, don't use this notation. Just stick it with this one. All right, so now we have this. We can easily do the same manipulation for the other one. For this one, all we do is first, let's calculate its magnitude, which is square root of 3 square plus 2 square. Well, that would be square root of what? 13. We can factor out the 13. Well, okay, so this one, it seems it's not a regular angle. So I can just write it like this, square root of 13. And then we will end up having 3 over root 13 plus 2 over root 13i. Okay, I messed up my picture pretty badly. But then I know that I can just rewrite it as square root 13 and then CIS, whatever angle it is. So I can just call this angle theta. So one of the angles is nice, the other angle is not nice. Once I know the two angles, I now know how to finish the multiplication, the product, right? I just add the two angles. So I just add theta to that 45-degree angle. So suppose it's somewhere here. So the new point will be here. And then I can further scale it. So in the end, the product between z when you express it like this, and then the w when you express it like this is the following. Z times w is simply equal to, you can just multiply the scale, the factors, the root 2 and the root 13. And then for the inside, this angle was theta, right? So it will end up being cosine of 45 plus theta, and then plus I sine of 45 plus theta. Okay, so this is a very bad handwriting, but I think you guys see where I'm going with this. All right, so, well, by now we realize that multiplication of complex numbers is the same thing as just rotating them, right? And I can go back to the initial question that I asked you, and we can easily do the business. Now, let's have a look at something very interesting. If multiplication is just addition, then suddenly we can start thinking about things like a square of a complex number. So suppose that our complex number is cosine theta plus I sine of theta. When I square it, it is just doubling the angle, right? Do you guys agree? So it is just the same thing as just doubling the angle, because it is, all I'm doing it is just rotating it, right? How do I know? Okay, a couple of questions. How do you know a theta exists such that such theta and sine theta are those specific values? They have to. Because if they are in the complex plane, they have to exist, right? So I think everybody would say yes, because as long as the number is somewhere on the complex plane, it will have a projection onto this thing. So once I divide it by its magnitude, so this is z, by dividing it by magnitude, I end up here, z over the magnitude of z. So there will always be a theta which yeah, will represent this in polar form. So that this will definitely always exist. And in fact, you can just take that z to the other side. So z can be represented as the magnitude of it times CIS theta. So you can always represent a complex number in such form. Yeah. All right. So yeah, we can always do that. So that was also, I think this was good for everybody. So we clarified something which I totally missed. So usually magnitude is very easy to handle because it's just a real number. As long as you understand how is the mechanics of the argument, life is pretty good. How about z cubed? Cosine of, yes, that would be 3. It will be tripling the angle, right? Sine of 3 theta. So basically what we are saying is if you are in the complex plane, and if this is the complex number z with angle theta here, z square is somewhere here. You just rotate it by that same angle theta. Z cubed will end up here. And then for those of you who are worried, hey, Dr. Nal, what if my number is just slightly outside? Let's say it's somewhere here, z. Well, it's still the same thing. So you have the theta here. When you square it, the angle will double. But because you are living outside the unit circle, this was the unit circle, right? Sorry, I here, -1 minus I. So you will just be pushed out a little bit. And then when you cube it, you will push out even further, z cubed. But the angles will always be whatever they are, right? So, and then you will further, so z to the 4. So do you guys see what's happening? So you are spiraling away from the center. Yes. But if your starting point was inside, okay, so for instance, what if you had a complex number with over here, w, then when you square it, so this is your angle, then squaring it will reduce its size further because its magnitude is less than 1. So this would have been w squared. Then you will have a w cubed somewhere here, w to the 4 And then, so it will spiral in all the way until like higher and higher powers, you will get closer and closer to 0. But if you are exactly 1, you are in an orbit, yeah, like a satellite, right? It's like a satellite, you keep circling around the unit circle, never falling onto Earth or never going out in space, right? That was one of my childhood, when I was like in high school and even before that. Well, I kept changing my mind, right? Even today, I have an interest on everything. So I think it's a curse of people who keep reading Wikipedia. When you start reading Wikipedia, and every week you change your mind about what you want to become as a professional. So when you start reading about history, you say, when I grow up, I want to be a historian. And then you start suddenly reading about chemistry, you say, hey, I will be a chemist. And then you start reading about physics, you say, you are going to be a physicist. So anyhow, one of the problems that I was thinking was the following one. So suppose that there's a hill, right? So this is a hill. And then you have these old school cannons, right? So suppose that, yes, there you go. The old school cannons. And I'm here holding a match. And then this had this thing. So, and I shoot. Well, when I shoot, it falls. The cannon, ultimately it will fall to a certain distance, d, right? Do you remember this? So it's horizontal. So initial shooting thing is horizontal, but over time it will just fall. Yeah. Okay, what if I shoot with a bigger power? My cannon is a stronger cannon. What will happen next? I should be able to, the horizontal shooting thing is still the same, but ultimately Earth will just pull it to itself, right? It will be a bigger distance, L, but ultimately it will fall onto Earth. Unless I shoot it strong enough that what? Okay, so yeah, that's how my interest in physics started. Okay, so pretend that I'm here, right? Technically, I'm shooting parallel to the tangent line here. There's a tangent line there. My initial shooting is just, yes. We'll try to see if we can escape the Earth. So first you shoot, you fall here. You shoot, ultimately you fall. You fall until you shoot it good enough speed where you hit yourself in the back. How did he die? He shooted himself. But how can it be? With a cannon. Is it even possible? Yes, sir, it is. Yeah. Yes, that's exactly the logic of satellites, right? Satellites, when they send a satellite up in sky, I mean, around the atmosphere, I don't know, let's say 100 kilometers outside the atmosphere, the way it is, the satellites are turning around the Earth, and they are orbiting around Earth pretty fast, by the way. They have to orbit at a certain speed, right? We proved it. If they don't orbit around a certain speed, they will fall onto the gravity. If they orbit too fast, they will spiral away, right? So there is this speed, which is the amazing speed, right? So not the amazing speed. So you have this speed that you want to keep turning around such that it has two forces. Earth is pulling in with a certain force, and then you circling around the circle, what happens? There's a push force. What they call it? The centrifugal force is the one which pulls, I think, right? And then the inertia is the one that, yeah, there are two forces, let's call it F prime, which pushes it. Yeah, centripetal and centrifugal. Okay, there you go. So the moment these two forces are exactly equal, then it's good. Yeah. Anyhow, I have no clue why I told you this story. I thought we were talking about complex numbers. Okay, so let's make it faster. Yeah, let's first do it small. Yes. Oh, so the spiraling of the complex number. Yeah, if the complex number is larger than 1, it spirals away. If it's less than 1, it goes all the way to the center. Yes, yes, yes. But wait a second. We can use induction, and we can prove it for the general case here, right? N theta plus I sine n theta. It shouldn't be too hard to use it induction. So suppose that this is true. Let's just use induction to prove the general case. So Zn plus 1, if you check this, so technically this is just Zn times Z. So we assume this is true, and let's see if we can solve it for n plus 1 as well. So this would be cosine of n theta plus I sine n theta times cosine of theta plus I sine of theta. And just, again, multiply them out. Cosine of n theta, cosine of theta, plus, and then we can multiply these two, and then the I squares become minus, right? So sorry, there's a minus sign there. Minus sine of n theta, cosine of theta, and then the imaginary part, I times, open parenthesis, sine of n theta, cosine of theta, plus cosine of n theta, sine of theta. But then wait a second, the first parenthesis is what? The real part is nothing but the sum, right? So of these cosines. So this is cosine of n theta plus theta, which is cosine of n plus 1 theta. Holy, that's good. Plus, so plus I, and then the same thing here. This is just the formula for the sum formula, the addition formula for sine of n plus 1 theta. Hey, we proved it for all integers now. So for all integer powers, we did it. Okay, so some of us are begging to tell you guys something. Okay, now I'm starting to get confused, or not confused, but so what type of function when I square it? Okay, so think about it. So we have this complex number z, which is cosine of theta plus I sine of theta. When I square it, it doubles this thing, right? 2 theta. So why don't I call it like f of theta instead? That complex number z, let's call it f of theta. And then let's call this one f of theta. I want to square it. So z squared is just f. What other function do you know when you square the function, it doubles its argument? Okay, let's try. So for instance, f of x is equal to x. If I were to square f of x, would it be equal to question mark 2x? No, f of x squared is just x squared. X squared is not equal to 2x. Okay, x is a failure. Okay, let's try x squared. So how about f of x equals x squared? If I square f of x, let's see if that comes out as replace x with 2x. It has to be 2x squared. Let's see if it works. F of x squared is just, well, based on this x squared, it's x to the 4. And then this one is 4x squared. Again, it fails. Okay. Okay. So some of you guys are suggesting we know one that works. Here, f of x, suppose it is 2 to the x. So if I square it, let's see. If I square f of x squared, it's just 2x squared, which is just 2 to the 2x. Hey, it is as if this is the same thing as f of 2x. Holy cow, that's exactly what this is doing, right? And that's exactly what Euler, about 300 years ago, he realized. He realized that, hey, I can replace this with e to the power I theta. Now, I'm not showing you, all I did here is to show you that it has to be in exponential form. But I'm not telling you like how to prove it. You need calculus to prove that, right? So this would be I to the power 2 theta. Do you guys agree? Yay! So this is yet a third way to represent a complex number. And it turns out it is more natural to do it this way, especially when there are angles involved, right? So for instance, if I ask you, so going back to the complex plane, the unit circle, I should say. So this is CIS, let's say that this angle is 30 degrees. This is CIS 30 or cosine 30 plus I sine 30. This one is CIS 45. If we were to write them in what? In Euler form, let's call it Euler form, e to the power I, it's customary to turn it into radians. So 30 degree would be pi over 6, right? Pi over 6 here. And then this one is e to the power I. This one is pi over 4. Hey, because I want to multiply them, let's just go ahead and multiply them. Multiplying these two complex numbers is just I to the power pi over 6 times e to the power I pi over 4. Hey, this is natural. It's just adding the angles. Do you guys see that? That's pretty convenient. Yeah, that's really good. So that's another intuitive way to understand why complex numbers are so, like, when you multiply them, you get this rotation business. All right, so far so good. Now, one of the people who got extremely excited about all this was Gauss. Well, obviously Euler was excited, but Gauss was also excited about that. Well, you guys know that the Greeks, they already knew how to draw a triangle, an equilateral triangle. Anyone can draw a triangle, right? But so they could, they also knew how to draw a pentagon, a regular pentagon, using just a compass and a ruler or a straight edge, right? Well, obviously, yeah, the square is too easy. Yes, they could definitely do that as well. Yeah, but then that was pretty much it. They were stuck, and they couldn't do much after that. So Gauss, when he was still pretty young, yes. Well, obviously hexagon, they could do it too. Yes, anything which is a combination of these, it can be done as well. Yes, they can definitely do a hexagon as well. But then Gauss realized, so I should say, okay. So let me be more specific. Let's say for prime side lengths. Here it's 3. Here the prime is a 5. They could not do it for any other prime. Let's say it like that. Until Gauss realized that he can do it for a 17 gon. Seriously? How in the world can he do that? Well, for that, let me just give you one more idea, and then we can directly dive into that. The only remaining idea is the following. I am not going to do all the details of Gauss's argument, right? So that's, yeah. But the idea is the following. Because by now we know how to take any power of it, right? So the powers like n theta here, n doesn't even have to be an integer, right? N can be any number. N only, sorry, n. So it might as well be a rational number, like 1 over n should be also technically possible, right? There's nothing wrong with taking 1 over n as well, which will simply be if z, okay, let's first write z first. If z is cosine theta plus I sine of theta, then z to the power 1 over n technically should be equal to cosine of, remember, z to the n, let's first do z to the n again. It's just multiplying the argument, the angle, with the exponent, right? So therefore z to the power 1 over n technically should be equal to this. What? Theta over n, right? So theta over n plus I sine of theta over n. There you go. Yes, I'm going to an interesting idea from here. Okay, so now I want to check, okay, there's something called roots of unity. I want to check all the roots of unity. It means the following. I want to find out all the solutions to these equations, basically, Zn minus 1, to these type of polynomials. I want to find all the solutions in the complex plane. Okay, for all n. Okay, let's start with this, and then we will find for any number. We should be able to find the cubic root of, or the square root of any complex numbers. But the natural way is to start with this one, right? So let's start with this one, for instance. Z minus 1 is equal to 0. What are the roots on the complex, on the unit circle? By now, I know that the root has to be on the unit circle, right? Because you take a complex number, you take it to exponent. If I'm not on the unit circle, it will, if z is more than 1, the magnitude, then it will spiral out. If the magnitude of z is less than 1, it will spiral in. So it has to be exactly on the unit circle. Yeah, this one is easy. Yeah, that one is, the root is here. Done. How about the next one? Z square minus 1, or z square is equal to 1, let's say. Where are the roots? Well, this one is easy too. This one is not even complex. Z is equal to plus or minus 1. That was easy, come on. So plus and minus 1, right? Plus 1, minus 1. That's easy. So anything that you can do with reals on the complex plane, you can still do it, right? So it's pretty convenient. So now let's start to our first challenge. Z cubed equals 1. Now this one is not obvious, right? So, well, we know one of the roots for sure. One of the roots is definitely 1 here. But technically, in the complex plane, we should be able to factor it out all the way, right? And the trick is just to use the formula that we have just learned. So let's just use the formula. The formula, by the way, has this fancy name, de Moivre's theorem. And usually, I always confuse de Moivre with De Morgan, right? De Morgan's theorem or De Morgan theorems. Do you guys remember this one and that one? So De Moivre's theorem is taking the powers of z to the power n, right? So this one just tells you that this is cosine n theta plus I sine n theta, or let me just call it CIS n theta. Versus De Morgan is just this one, right? A union B is equal to like the sum A plus something like that, right? Set theory. Yes, this one is from set theory. Yes. All right. Well, why don't we just reuse De Morgan's theorem to do it then? So we have z cubed equals 1. I can just rewrite 1 as a complex number. So how can I write 1 as a complex number? In the complex plane, how can you, sorry, in polar form, I should say. How can I write it in polar form? Yes, it is 1 plus 0i, but in polar form or in trigonometric form, yes, that is just CIS 0 degrees. Well, or you can call it CIS 360 degrees, right? It's probably more convenient to write it as 3IS 360 degrees in this example, right? Do you guys agree? Oh, suddenly I can use De Moivre's theorem again, right? So I can take the cubic root of both sides, boom, take the cubic root. So z as a result on the left-hand side. On the right-hand side, the cubic root power, it just comes out in front of the angle as a multiple, right? CIS or cosine theta plus I sine theta. So CIS 1/3 of 360. And that's CIS 120. Holy, we found another root. Okay, so far I have been using a very, very sloppy language, right? So I will just formalize it in just a few minutes. But alternatively, I could have, instead of writing it as CIS, for instance, if I wrote it as CIS 0, then taking the cubic root would have given me another CIS 0. If I wrote it as CIS 360, it gives me here. If I can, alternatively, I can write one as CIS 720. How about that? Why not? So taking the cubic root of both sides, so that would give me z is equal to what? Yes, CIS 1/3 of 720, which is CIS 240. Yay! There you go. So we are able to find all three roots. It technically, once you find one of the roots, it's very easy to find the other two roots. Do you guys know how to find the other roots? For instance, let's solve another one. If I ask you to find all the roots of this equation. So, well, two of them are very easy to find, obviously, right? So one definitely works. So if you have one of the roots, you can easily find all the remaining three roots. How do you do that? Yes. So all you do is, because this whole angle is 360 degrees and we are dividing it by 4 in a sense, for instance, z to the 4 is equal to, we can write it as CIS 360, for instance. So as a result, taking the fourth root, that would be CIS 360 raised to the 1/4 power. And that is just CIS of 90 degrees, right? That will give me another root. And then alternatively, you can replace, instead of writing one as CIS 360, you can write it as CIS 720. Dividing it by 4, that will give you this and that. But do you guys see the pattern? So when we took the cubic root, this was the locations of the roots. 120 degrees, 240 degrees, and 0 degrees. Here, when I found them, the angles are 90 degrees, 180, 270 degrees. Yes, you always get regular polygons here. In this case, you get a square, a regular polygon inscribed inside it. Here you got an equilateral triangle. Do you guys see that? So yes, so therefore life is pretty easy after that. All you need is the first root. Once you find the very first root, Then the rest is just completed into a polygon. So just as an example, let's solve a harder problem now. Z to the power, say, okay, let's still solve Z to the power 4 is equal to, say, for instance, cosine of 45 plus I sine of, oh no, that wasn't my intention. Let's say Z to the power 4 is minus 1. Okay, there you go. So what are the roots of this one? Z to the power minus 4. So Z to the power 4 is equal to minus 1. Let's solve this one. What are the roots of this one? Square root of minus I. So what is the square root of I? Yes. Yeah, you can calculate square root of I. Yes, that's correct. You can take the square root of both sides and then further take the square root of both sides. The first time you take the square root, you get that Z square is equal to plus minus I. And then further you take the square root. So you get plus minus square root of I, right? So plus minus I. And so you have 4 roots here. But this is not a very convenient way to do it, right? Why don't we just do it the way we learned together? Z to the 4 is equal to, let's rewrite minus 1 using the polar form. So minus 1 in polar form is equal to what? Cosine of which angle plus I sine? Yes. And do you guys agree that this is cosine of 180 plus I sine of 180, right? So now I can just go ahead and take the 1/4 root of both sides. So therefore Z will just be equal to cosine of 180 plus I sine of 180, the 4th root of it. And now Z is technically equal to, well, this is only one of the representations. Alternatively, I could have written it as cosine 540 plus I sine 540, right? But anyhow, my goal is just to find one of the roots and then complete it into a polygon. So that is just cosine of 45 plus I sine of 45, right? 180 divided by 4. Hey, I found one of the roots. This is one of the roots. Oh gosh, I thought it was different color. There we go. All right, so this is one of the roots. So this is minus 1. One of the roots of minus 1 is this number here, Z. Well, the other roots are here. You complete it into a polygon, but because this is a 45-degree angle here, it will nicely give you this square here, right? Because you complete it into a square because this is a 4th root. So you will find Z, well, okay, so this one is, what is the angle here? 135, right? So this whole angle is 130. It's 45 plus 90 degrees. And then another 90 degrees. Keep adding 90 degrees to it. And then add another 90 degrees. So these would be all the roots of this. And obviously, they would be all these weird numbers. Yeah, so therefore, yes, exactly. So if you want to write it in the regular way, yes, that would be that. Yes, that's only one of the roots. The other roots is, yes, so you just keep adding pluses and minuses in front of them. Okay, let me actually do it. Plus, minus, plus, minus. But in all 4 combinations. Yeah, so you can call it Z1 if you want. We can call this one as Z2, Z3, Z4. Okay, so let me show you how the Greeks were able to draw the, that's equal to what? The square root of I, yes sir. Square root of I is nothing but this. Okay, so check this out. So if I is here, okay, let me give you the trick. So, and it makes sense. So if you have any number, let's say I, for instance, I is here. If you want to calculate the square root, because its angle is 90 degrees, the square root is just half the angle, right? So that would be I to the power 1/2, right? Do you guys agree? So that would be the square root of I in a sense. You guys can even calculate I to the I. It's not too hard to calculate it. Or for instance, anytime you have from now on, for instance, the example that we just solved, when we wanted to find the 4th root of it, all you do is you divide the angle, which is 180 by 4. There you go, that's the 1st root. And then because you are doing the 4th root, you know that there will be 4 more roots by just completing it into a foregone. And there you go, you are done here. Z2, Z3, Z4, very convenient. So for instance, if I ask you, what are the roots of this monster over here? Z to the 5 is equal to -1. All you do is just find one root. Which root is the convenient one to find? Well, one of the roots is obvious. Yeah, -1, yes. You can start with -1. Wait, does this thing work? I think it does, right? And then you can find all the remaining, so how do I do it? Yeah, like that, and like that, yes. Yeah, because the angle was 180, divide 180 by 5, yes, that would give you 36. Alternatively, you could have started with 36 degrees here, add 72 degrees to it, add 72 degrees, add 72 degrees, and add 72 degrees. Finally, adding another 72 will get back to the original. So, so there's alternative ways, like you can, okay. So let's go back to the Greeks. So the Greeks wanted to draw the pentagon, right? So how do they draw the pentagon? Drawing the pentagon is not easy, by the way. Drawing an equilateral triangle is easy, but the pentagon is hard because you need to somehow figure out a way to measure a 72-degree angle, like cosine 72 or sine 72, right? So the Greeks, they started with this, I guess. No, they didn't do it this way, obviously, right? So z to the 5 minus 1 is equal to 0. Well, complex numbers, they started way later, like 14th, 15th century. Yes, so one of the roots is very easy, z minus 1, and then we have z to the 4 plus, you guys already know how to do this, right? So how to factorize this. The way, do you know how I remember this one? Yeah, I usually remember it from the partial geometric sum. Yeah, the geometric sequence. Yeah, because remember that the sum, this sum here in general is z to the 5 minus 1 over z minus 1. So, and then you can cross multiply. But this should work. If you factorize, like if you FOIL this out all the way, that should give you back to this thing, which is okay. So this one will give you our unique real root, right? So, and then all the other complex roots are here, but I need to find a way to factorize this monster. So how can I find the roots? Just using the quadratic formula. So pretend for a minute that we don't know about the trick that we just learned, right? So how you, so we're going to figure out a way to calculate the cosine of 72 degrees. So I need one root. So far the root that I found is not very convenient for me. Well, I mean, it is convenient, but it's just one of them. So far I know this root. I want to see at least one more. So I need this angle over here. Well, I know this angle. It's 72, but I want to figure out what is the cosine and sine of it, right? Using just, yes. Okay, yeah, some of you guys already seen it before, I think. Well, the trick is the following. There's a tricky way to solve these type of equations. I don't know if you've ever seen it before using polynomial tricks. The trick is a substitution. But before we use the substitution, we can just go ahead and, because it's a symmetric form polynomial, do you guys remember how to solve symmetric form polynomials? You divide by, so I want to divide this by something. What should I divide it by? Yes, divide by, yay. Well, at least several people have seen this trick before. Yes, divide by z squared. If I divide that by z squared, I get that, because that I want, this thing is still equal to 0, right? Either the first the first factor is 0 or the second one is 0. So still 0 after division by z squared, it shouldn't matter, right? So I have z squared plus z plus 1 plus 1 over z plus 1 over z squared. Hey, now I can group them together, right? So I can group them as z squared plus 1 over z squared plus z plus 1 over z plus 1. Suddenly, I feel like completing this into a square. Z plus 1 over z square. Well, I also need to subtract 2 from this. I will do it in the end. Plus z plus 1 over z. And then I still have a 1 minus 2. So that's a minus 1 now. Aha. So I can just call z plus let z plus 1 over z. You can call it as w. So suddenly we need to solve this equation, w squared, oh gosh, hold on. w squared plus w minus 1 is equal to 0. Hey, that's easy to do. Not minus 3, minus 1. Why? Because I have a minus 2 from this one and then a plus 1 from this one. So quadratic formula, right? If I use the quadratic formula, minus b plus minus square root of delta. Delta is 1 minus minus 4 times. So it's, yes, this is a root 5, right? Basically, after you use the all divided by 2. Hey, yes, we have the 5. So I will use the plus 1. And guess what? So as a result, z plus 1 over z is equal to root 5 minus 1 over 2. But wait a second. Earlier, I said that on the unit circle, where is 1 over z located? On the unit circle, where is 1 over z? Yes, it is just the same thing as z bar, which is the reflection on the across the x-axis. Yes, this is where 1 over z is. So z plus 1 over z is this number, but I know how to add these two using the parallelogram technique. Z plus 1 over z, because they are reflections of each other, they will exactly fall onto here. Z plus 1 over z. Aha! And as a result, the x-coordinate of z will be half of that distance. Do you guys agree? So this implies that the x-coordinate of z will be, if you guys want, how should I do it? The cosine of 72. Okay, let's directly go to the bottom of that. So cosine of 72 as a result is just root 5 minus 1 over 2 over 2, so which is over 4. Do you guys agree? And that's it. So interestingly, the Greeks already knew if you have two distances, how to add those distances, how to subtract the distances, how to square root, how to reach the square root of distances. So for the Greeks, it was just a simple exercise to construct a shape with these dimensions. Once they have this secret number, life is pretty easy. Wait, yeah. And what? And then that's it. Once you know okay. So as a result, there's an algorithm here, right? The algorithm is this. So first measure that distance, mark it here, which we know it should measure this much. So mark that there. And then draw a perpendicular until you hit the unit circle there. And then that's it. So you have your first side here. And then from there, you can just replicate what you just did. Keep replicating until boom. So you have the full pentagon. So in the case of Gauss, he figured that, well, I don't know how he did it. He used the 17th roots of unity to realize that cosine of 360, unfortunately 360 is not divisible by 17 the way that 360 is divisible by 5 and you get 72 nicely. So they came up with this weird, extremely weird expression. I mean, he came up, sorry. Gauss did it, 18th century, I think, square root of 17 plus 1 over 16 square root of 34 minus 2 square root of 17 plus 1 over 8 square root of, okay, so this part is weird, plus, but decidedly a radical, right? So there minus square root of, there's two more, 34 minus 2 square root of 17, and then inside that one, we have minus 2, 34 plus 2 square root of 17. There. Once he had this formula, he was able to, well, I think on Wikipedia, if you check on Wikipedia, there's a 64-step construction. Oh, Numberphile has it too. Numberphile has a great video about the 64-step construction of it. Once I watched it on Wikipedia, just search 17 gon on Wikipedia, you will see step-by-step 64-step construction, and then do it at home. You will appreciate it. If you, I mean, so it's a really good construction. When does class end? At exactly 3 p.m. Almost there, 9 minutes. All right, so the rest of the time we can just entertain ourselves with some kind of interesting examples. For instance, does anyone remember even the formula for cosine of 3 theta? It has a formula in terms of cosine theta. Wait, did I skip something? I might have. Yeah, I'm just going all over the place today because it's complex numbers. Yes, so there's a weird formula, a cubic formula for that. But now that we know the de Moivre's formulas, we can easily use it to do it, right? So all I do is if I start with cosine, a complex number like, well, okay, so let's start with this cosine 3 theta plus I sine of 3 theta. Well, technically, this is the same thing as cosine theta plus I sine of theta cubed, right? And I can just use the binomial expansion, right? The cubic expansion. So that's just cosine cube theta plus 3 cosine squared theta sine theta. And then there's still an I somewhere there. Plus 3 cosine theta plus, sine square theta, sine square theta, I square, and then finally plus I square sine cube theta, right? But all I need is really the real part. I don't care about the imaginary part. So therefore, as a result, cosine 3 theta is equal to, well, the real part has this portion, cosine of cube theta, and then it also has this portion because I square is just -1, minus 3 cosine theta sine square theta. Done. Oh, I messed up already. It should be I cubed. Oh, yeah. This one's a cubed. Yeah, sorry for that. Thank you. There you go. Well, but the imaginary part will give you the formula for sine 3 theta. For the cosine 3 theta, there you go, cosine cube theta minus 3 cosine theta. And if you want to express everything in terms of cosine theta, this is just 1 minus cosine square theta. So as a result, that gives you the formula, what? 4 cosine cube theta minus 3 cosine of theta. There you go. In a similar way, that you can just looking by equating the complex parts, you can as well find an expression for sine 3 theta as well. So it's basically an expression in terms of sine theta as well. It's not minus. Why not? It's minus because there's this I square here. I square means -1. Yeah, this is a plus, that's a minus. So yeah. Okay, so yeah, so that's good too. Well, we can, there was this old ARML problem. I don't know if you've seen this problem before, ARML. Let me just ask you that question and let's call it a day for today. Let me see if I can figure out. Yes, the question says this: on the complex plane, we have a parallelogram, oh shoot, how do you spell parallel? Parallelogram. Okay, there's another L. Okay, parallelogram with the following vertices. Oh, sorry, I think the first vertex is the origin. 0, Z, 1 over Z, and then the last one, obviously, by the parallelogram rule. What should be the last one? Okay, in terms of, so what is it? The last vertex. 0, Z, 1 over Z, and yes, it has to be the sum of the other two. Yes, 1 over Z. There you go. The question says the following: this parallelogram has an area equal to 35 over 37. And then the question is, find the smallest value of the following. D is the minimum value for the absolute value of Z over Z plus 1 over Z. There. Yes, if you remember our integer-sided triangles from last week, we know that 35, 37, 12 is a right triangle, right, where 37 is the hypotenuse, right? 37 square minus 35 square is just 37 minus 35 times 37 plus 35, which is 72. 72 times 2 is 144. The square root of it is just a 12. Yes. So therefore, there's something fishy there. I can imagine a right triangle will pop out of nowhere, right? So, okay, so let's first draw that, like just having a visual in front of you, right? When you can visualize things, it's always good. Well, yeah, so we have this complex number, which is somewhere. It doesn't have to be on the unit. Oh, well, why did I draw the unit circle? Yeah, it doesn't have to be. Actually, it is not on the unit circle. Okay, so there you go. So suppose that you have this complex number z here. So I think we already discussed 1 over z will end up being somewhere on the reflection line, right? So somewhere on the reflection, this is where the z bar is. So 1 over z is somewhere over there, right? 1 over z. So therefore, our parallelogram will look like this in the end. Something like that. Yeah, so this is the shape of our parallelogram, where this is 1 plus 1 over z. All right, so, and if you want, yeah, okay, so we can call these angles as theta and theta. So z as a result is r times, or whatever is its magnitude. Okay, I have no clue about its magnitude either. Okay, so whenever you don't know the magnitude, you can call it like magnitude of z times cis theta, right? Cosine theta plus I sine theta. All right, so that's what z is. Okay, and for 1 over z, we can write it as 1 over, like we did earlier, z squared, and then z bar. Well, that's fine too, so I don't want to go further. But let's, how do I find make use of the area? How can I calculate the area of the parallelogram? One of the vertices at the origin. Yeah, so I can definitely, so the magnitude on this side is a z. The magnitude on this side is 1 over z squared. Do you guys see that? As a result, I might as well just use, you know, the area of a triangle. One of the alternate formulas for the area of a triangle is the one which uses these sides C and B, and then this angle alpha. So it is 1 over 2, so the area, ABC, let me remind you of that. So the area of triangle ABC is just 1/2 B times C times sine of alpha, right? Yes, we might as well just use that formula and set it equal to 35 over 37. Let's just do it. Yes, sine area formula, as you guys said. So 35 over 37 is simply equal to 1/2. The magnitude of one of the sides is z. The magnitude of the other side is 1 over z squared. And then the sine of the angle between them, sine of 2 theta. Okay, where did I find the square? Where in the world did I find it? Yeah, that is not a square. It's, yeah, someone kept telling me it's not a square. Yeah. Sorry for that. There's no square here. Yeah, oh my gosh. Okay, sorry for that. It's just 1 over z times. Yeah, check your notes above, like check the video. We did it earlier today. So, okay, so there's no square here. Yeah, there you go. So these two cancel nicely. Yeah, so there's no square there. Yeah. Okay, and wait a second. That's the area of the triangle. I need to multiply by 2. Oh gosh, you guys kept telling me that, right? Times 2, sorry for that. The 2's also cancel. Yes, finally we find sine of 2 theta is 35 over 37. How convenient, right? From yeah, so that's good. So, but how does this help me establish the location of this monster over there? What can I do now? To find, the question is asking for what? Let's go back to the question. The question asking for the least magnitude here. So let's draw that magnitude. Okay, there you go. So the magnitude is really this segment over here. So we want to find the minimum distance of this here. Yes, one way to measure this distance is what? Now that I know what, yes, I can use law of cosine, right? I can use law of cosine on which triangle? For instance, I can use law of cosine on the triangle 0, 1 over z, z plus 1 over z, right? If I apply law of triangle, let me draw this. There you go. On this yellow triangle, I can easily calculate d. You might worry, hey, Dr. Nal, wait, how can I do that if I don't know this angle over here? Do we know this angle? Yeah, so we need for law of cosine. Yes, we do, right? Because it was a parallelogram after all. Yes, it's 180 minus 2 theta. Yay. Yes, that's it. So now let's go ahead and just finish this problem, monster problem. Okay, so law of cosine next. Law of cosine. So d square. And obviously we want to minimize it. The question says the smallest. D square is what? The magnitude of the 1 over z and the magnitude of this part. Wait, this part is the same as z, right? So therefore, this and then we need to square them. So z square plus 1 over z square plus, or sorry, minus, plus, minus 2 times z times 1 over z times cosine of, well, okay, the plus minus, we will adjust it in just a minute. 180 minus 2 theta, right? But cosine of 180 minus 2 theta, so d squared is equal to, okay, so we have this z squared plus 1 over z squared business. Actually, I can write it like this. It's possible to do it. You can practice it, but yeah, you can write it like this if you want. And then we have minus, so the z and the 1 over z here will cancel. So we will be left with minus 2 times. Cosine 180 minus 2 theta is equal to what? Cosine 180 minus 2 theta, is it minus cosine 2 theta, is it? Okay, so which means minus minus, we get a plus there. Plus 2 cosine of 2 theta. Okay, so you guys need to use addition formula. So make sure you convince yourself that that's the case, okay? So, but this sign has turned into a plus now. Now the question says minimize this. How do I minimize this? What is a good way to minimize? What is the minimum value of, wait, I can split this, right? Yes, because finding the minimum of this one is extremely simple. What is the minimum value of this monster over here? Yes, and then figure out what is the minimum value of this monster, do it separately. It turns out this number here is always greater than or equal to what? Yay, 2. It has to be. Because if z was on the unit circle, the minimum situation, z and 1 over z, they will be just on the unit circle. Their magnitude would be both 1. Yes, that's called AMGM inequality. That's correct. So if you apply AMGM here, you would have gotten, okay, remember AMGM, right? X plus y over 2 is greater than or equal to square root xy. So if you replace x with absolute value of z squared, replace y with absolute, so 1 over absolute value of z squared, and so from there you will immediately get that greater than or equal to 2, right? So let me just show it to you, and then we will, that's it, then we end the class. So z squared plus 1 over z squared is greater than or equal to 2 times, I just moved it to the other side, z squared times 1 over z squared. All right, so the z is outside, the square is outside. All right, square is there, so these will cancel and that will be a 2. Yes, now finally, what is the minimum value of this? Well, it turns out we already calculated that. If sine 2 theta is 35 over 37, necessarily cosine 2 theta, cosine of 2 theta is plus or minus 12 over 37. You guys can just complete it into a right triangle. And then from there, we are done, right? So now the question, as a result, d squared, the smallest value of d squared, we need to pick the, oh, sorry, 24. Oh, 24, because, oh, because there's a 2 in front of it. Yeah. So yes. So therefore, we will be using 2. The minimum value will end up being 2 minus 2 times, because there's still a 2 there, 12 over 37. So this is just 2 minus 24 over 37, which is equal to what? 74, 50. 50 over 37, that's the minimum value. And because we picked the negative one, so you can imagine that the parallelogram does not look like that. So the angle theta, 2 theta actually, is an obtuse angle, right? Yeah, so this is a quick application of this. Unfortunately, the problem is directly given in the complex plane. If they reworded the problem such that it's not in the complex plane, but on the Cartesian plane, it would have been interesting to see, oh, there's a plus. What's a plus? No, it's not a plus. Plus, the question says minimum. Find the minimum one. So we have an option to use whichever angle we want. We decided to go with the negative one, I think. Yes. Awesome. So yeah, that's pretty much it. Yeah, so if you guys are in middle school, probably this material is a little bit advanced, but this was our last week and I wanted to share this with you guys.